memories and also look into tests of the nature of compact objects and tests of the Norrie theorem. What I want to do in this lecture is to first go through some parameterized tests of GR. In particular, I will focus most of it on tests, well, actually almost all of it, on tests in the inspiral, essentially. And how we can do it or we can try to do it in a sort of agnostic way. And then also linking with this topic, and also because there has been questions and it's a topic that a lot of people are interested at the moment, I'm going to try to tell you something about environmental effects and going beyond the approximation that binary black holes live in vacuum. And in particular, because this is so this is a topic that is interesting not only from the point of view of astrophysics, but also there's been interest in this topic also for the purpose of searching for dark matter. So I will tell you about it. Okay, so but before going there, let me just remind you this diagram that Suzanne already showed. That essentially gives you a picture of how you can modify gravity, or you can modify GR in particular. So GR here, as Susanna was telling us, is basically the Lovelock theorem. So the Lovelock theorem is a theorem that tells you that GR is a sort of unique theory of a metric tensor in four dimensions that satisfies the weak equivalent principle, etc. And so when you want to modify GR, you can do it in many ways, in particular adding extra fields, going to higher dimensions, breaking some symmetries of the theory, etc. Although in this way of writing things, this looks like there's not that many theories. In reality, all of these, when you start breaking GR in this way, you start having really a lot of theories, right? And it's really unpractical to try to work with each one of these theories and try to do tests and test them and constrain them and perhaps rule them out. So the big question is actually how can you test all of these, right, in a practical sense. And so Susanna already also told us a bit about that, but I'm going to go through it again because I think that's quite an important point. How exactly you can test gravity. So there's been two approaches that have been used. In particular, you can just pick a theory, make predictions with this theory, make your calculations, and then compare with the data that you have available. And of course, this has the advantage of this approach is essentially if you are able to do these calculations, assuming you can do these calculations, you might get stronger constraints on the parameter that you want to constrain because you're actually making predictions on a single parameter. Let's say, for example, your theory has only an additional coupling constant, for example. So whatever constraints you do with gravitational waves, with solar system, etc., will always be on the same parameter, and that could allow you to constrain better the parameters of interest of this theory. In particular, if you do predictions with a given theory, you might end up finding, for example, smoking gun deviations from GR, which might tell you exactly what kind of deviations I want to look at. So of course, it's always essential that you actually do this exercise to try to see if there's something very different from a given theory from GR that might allow you to not only constrain, but perhaps rule out completely the theory. And more importantly, I think, or at least quite importantly, it is if you really look only at a given theory, it's very easy to actually combine many constraints. For example, in gravitational waves, combine constraints from many events. For example, if you have a single parameter, then combining constraints and constraining better and better your parameter is very easy to do. It's just multiplying your posteriors essentially for the given parameter that you're constraining. And also you can easily add not only gravitational wave tests, but also tests coming from other areas, for example, from cosmology or solar system. Which I should say is something that sometimes in people working on alternative theories, they tend to, I take my theory, I only test it in the strong field, and I forget that this theory might already be kind of rolled out in other contexts, right? I mean, we should be careful about looking into what is already constrained just from all kinds of tests. The main disadvantage, of course, of this approach is that, as I was trying to tell you, And as Suzanne also already pointed out, there's really too many theories. There's no, let's say, sufficient people and sufficient PhDs to do all the calculations that we need to constrain all the theories that exist that have been put forward. And in reality, I will say, in general, there's no real motivation to just choose one of these theories over others and just focus completely on these theories. I mean, a lot of these theories, they try to sometimes solve some fundamental problem. Let's say when you add higher curvature terms in your theory, this is mostly motivated from quantum corrections. If you think about your GR as an effective field theory, where you add up higher curvature terms as in an effective way. So these, if you are interested in quantum gravity, you might pick up these theories, for example. But in practice, there's no real difference between these theories and other theories that, I don't know, like massive gravity, for example, that adds a mass to the gravity. I mean, where massive gravity originally was motivated mostly to explain dark energy, for example. Well, originally it was more theoretical, but then early 2000, people started to be interested in it to explain dark energy, which is also a problem that we know. So, I mean, for example, these are two examples where there's no real theoretical motivation for me to focus on one theory over another. So that's a real problem, let's say, in terms of what to actually do. And more actually in practice is that in reality for a lot of these theories, so just in GR you've seen already many talks on waveform modeling, right? And you see how complex it is to actually get to end up with a waveform model that you can use against data. And in reality, there's no theory that we know of where we are at the point of actually building a waveform model like an UOB model or phenom model that we can compare with data. So we have simulations, numerical simulations of binary black hole mergers in some theories. We have some predictions from PN in some theories. We have also predictions of the ring bound from some theories. But putting all of this together takes a lot of work. And honestly, not always well motivated to spend, again, a PhD lifetime to actually build a model for this theory. So you might try to do it just as an example, but building, it really takes a lot of work. So it's actually a big disadvantage of going through this approach. So right now, most of the tests that you might see, for example, in LVK papers are actually what we call theory agnostic, right? So where you consider model independent, or at least sort of model independent deviations from GR. So Suzanne already mentioned the PPN, this parameterized post-Newtonian approach. So this is mostly used for solar system tests. And I will focus on these PPE, so parameterized post-Einsteinian approach. So you will see what exactly it is. And there's also been approaches based on effective field theory methods where you add basically to your action of GR, you add generic terms in the action and you try to constrain these actions. I'm not going to talk about this, but I think it's also an interesting way to do it. But the advantage of this approach is because in general it's easy to implement. It's basically you add some parameter to your waveform, for example, and just try to constrain this parameter. Ideally, you can build these model independent deviations in a sort of generic way that you can, with one single parameter that I'm constraining, then I can map to different theories and try to constrain as many theories as I want. That's, of course, in an ideal scenario. It's not always easy to, it's actually not completely possible to build complete generic model independent deviations from GR because some effects are actually not, let's say, for example, in a lot of these approaches, we assume that deviations from GR are necessarily perturbative, so they are necessarily small deviations from GR. So that might not always be true for some effects. So you might be missing some effects by doing that. So you end up only doing this because it's practical, let's say. But the main disadvantage of this approach is that, you're considering deviation from GR, as you'll see, for example, in the PPA approach, there's many parameters that you want to constrain. And if you do a Bayesian, analysis, in principle, you have 7, 8 parameters that you want to constrain, and how do you do this in practice in a practical way might become an issue when you start adding a lot of parameters, and in particular, if you start adding a lot of parameters, you can fit anything, right? I think there's this theorem that says with 4 parameters you can fit an elephant. And another disadvantage, as I will show you, for example, for the PP approach, mostly focus only on doing these tests on parts of the waveform. Either you do it in a ring DOM or the INSPAL, but because it's not really a theory, right? So you're just adding random parameters in some sense, you cannot really use the whole information that is in the waveform in one single fit in some. And as I was saying, it doesn't necessarily capture all effects. Okay, so before going to the PPE, let me just remind you some of the effects that you have when you go beyond GR. So perhaps the one that you've, well, I think you're already, someone, I think in the waveform, from what I've seen in the slides, you're already, this was already mentioned, but so in GR you know that you only have two polarizations, so H plus and H cross. But in general, for generic metric theories of gravity, so theories of gravity where you have a metric tensor, you can have up to 6 independent polarizations. So in GR you only have these two, so the cross and plus. And if you go beyond GR, generically you can have up to 6, so you can have a vector mode and 2 types of scalar mode. So these what is called the breathing mode and the longitudinal mode. That, of course, is not, so in, for example, if you have in scalar tensor, in general, you will have only H plus and cross, and in general, one of these two, I think, in general, you end up with the breathing mode. For example, in massive gravity, in at least the most standard one, you only have 5. I think there's one, yes. No, here actually, there's 2 modes here, so there's 2 vector modes that are represented here. So in massive gravity, for example, you end up with 5 degrees of freedom. There's one of these scalar modes that you kill that is not there, for example. But anyway, more generically, that's the type of phenology that you will have. Although there's interest in this test of polarizations, I will not talk about it, because if I have to be extremely honest, I don't think it's the best way to constrain GR. So most likely, even if you detect an extra polarization, you will most likely be able to constrain the theory already much better through other approach. An example would be, for example, in scalar tensor. So in scalar tensor, if there was scalar radiation that will be strong enough for you to detect, longitudinal, one of these scalar modes, for example, this will mean that you're also having like scalar emission in your binary, and which will mean will change considerably the decay of your binary, and most likely you can constrain it much better just looking at the gravitational wave or the H plus and H cross and see all the phase change over time. And probably because you detect much better H plus and H cross, you will most likely put much better constraints using that. But it's, let's say, in principle, is a fundamental test that you can do to test whether you only have H plus and H cross in your detectors. Okay, but some additional channels that beyond GR, so I will talk about this one, for example, when you have additional energy losses. So if you're adding additional degrees of freedom, for example, a scalar field like Susan talked about, you'll have additional channels for energy loss, and that will change all your binary will decay over time. You can also modify the dispersion relation of your wave equation, of your graviton, if you want. So, for example, if you add a mass to the graviton, I will show you an example. Yes, go ahead.
I was just wondering, the second one, do you think we have a chance to distinguish this from like an environmental effect?
That's a good question. I think in some cases, yes. But I cannot say, well, actually, I think in my last slide I have a point exactly on that. Okay. I'm not exactly sure whether we can completely always distinguish. Because, yeah, the idea is similar. You modify basically all your orbit decays. But so you have also the modified dispersion relations, for example, adding a mass to the graviton, violating Lorentz symmetry, etc. Something else that can happen, so in particular there's a theory called dynamical Chern-Simons where you have parity violation. So it's essentially what this does is that it makes H plus and H cross travel at different speeds, and it leads to these amplitude birefringence. This is something that can happen also for electromagnetic waves when they are traveling through some media, where it makes the two polarization of the electromagnetic wave travel at different speeds, and it leads sometimes to the rotation of your field, if you want. So anyway, this can happen in some theories of gravity. And we already discussed also these cases, but I added them for completeness. Of course, if you modify gravity, you can start having airy black holes, modify the ring down, modify the quasi-normal modes, start having non-zero tidal love numbers for your black holes, etc. Okay, that said, you should also distinguish between, when you do a test, you should distinguish whether there's two types of effects that you can test, right? So in general, so you're interested, for example, you have your binary black hole, and locally you might change all you generate gravitational waves. For example, if you have dipolar emission, you are modifying essentially all these binary decays, right? But for example, in a cosmological sense, for example, imagine that you have some different dispersion relation. As this wave propagates, until us, it will also be modified, so its profile will be modified with respect to GR. So there's also effects on the propagation. So depending on the theory, you might have both effects appearing. In a lot of theories, for example, they only modify generation. In some theories, for example, I will talk about the example of massive gravity. That one is quite subtle, I would say, because in general, most tests that are being done with massive gravity, they only consider the fact that if you have a mass to the graviton, you change the propagation of your wave. So the different frequencies of your wave will travel at different speeds, and this will modify the wave. But in reality, so from the theories that we know of massive gravity, they might also change generation, but the theory are so complicated that no one actually has done simulations of proper simulations of binary black holes. So even though we are assuming that we constrain things only to propagation, sometimes we have to admit that without knowing actually how these waves are generated in these theories, we might be being extremely conservative. Perhaps just from the generation you will completely exclude those theories. But so let's say if we could do it, ideally we will compute generation in a given theory and then test all these things propagate. In practice, we don't always do it because we cannot always do it. Sometimes the calculation is just too hard to do. Okay, to give you an example of how you can modify the generation of gravitational waves, so the typical example is dipole radiation. And so dipole radiation, normally it's introduced in the context, for example, of scalar tensor theories, but it's nothing weird, right? If you have just if your two black holes will be charged, for example, if they have some electric charge, they will also, in principle, emit dipole radiation. And that is basically because, so the reason why you don't have dipole radiation in GR is because you have mass conservation and linear momentum conservation. So in particular, the dipole moment in GR is related to linear momentum. And so because the power emitted is always time derivatives, you end up, because the linear momentum is conserved, you end up with no dipolar momentum, no dipolar radiation in pure GR. But if you had just an electric charge, right, because a dipole, an electric dipole emits radiation if you shake it, that's how you emit most of light that you know of, you will end up with also dipolar radiation. But of course, because we know that the electric charge might not be important, at least in the context of binary black holes. If we see some dipolar radiation, most likely it's coming from something like a scalar tensor theory or whatever theory that allows dipolar radiation. And just to give you just a reminder, so this at least at the Newtonian order, the way you will do this computation, for example, is so if you only modify generation, so basically here I'm saying that you only modify all your orbit decay by adding an additional term that depends on the dipole. So this in GR, for example, so you've seen this formula, I believe. So this is the quadruple formula that in GR the gravitational waves are emitted due to time-dependent quadruple moments. If you have some dipolar emission, you can also compute your dipole moment and compute the second derivatives, and you get something that goes as v over c to the 8. Notice that this power here is 2 orders of magnitude smaller than this one. And so if you use these equations, something that you notice immediately is that because you're adding an extra channel for dissipation here, your dipolar radiation will force the binary to spiral faster in general. And also something important is that in a very early spiral, when the velocities are very small, this term will dominate over this term. So scalar radiation, dipolar radiation has always the effect that it's more important in the early spiral compared to, so in the early spiral, it might dominate actually over the quadrupolar emission. So if you have a long spiral, you might be able to constrain it better than with a short event, for example. And so in practice, the way you actually detect this is because the phase of your gravitational wave is sensitive to the rate at which you spiral, as you know. So if you compute the time derivative of the gravitational wave frequency, you can write it in terms of these quantities, in terms of the orbital, at least in the post-Newtonian sense, of the derivative of the rate of change of the orbital energy. And here, there's basically dependence on this orbital energy. And so if you plug so the gravitational wave phase essentially goes as two integrals of the derivative of the frequency, of the gravitational frequency. And if you plug in these numbers and you try to do these calculations, you will see, so the first term is essentially the term related to gravitational emission. So it's a Newtonian term that you might have seen, I think, in one of the lectures. And this term will create an additional term, so it depends on some overall parameter that will depend on your theory. And we'll have an additional term here, this power, that relative to this one, it's what is here, you would call it a -1 PN order effect, because it's v to the -2, v to the -2 small, so there's a factor v to the -2, sorry, with respect to this term. So at smaller frequencies is more important. At smaller velocities. Any question about this? So this is an example. So this was an example of generation, and what I mean by propagation effect is essentially imagine that you modify the dispersion relation, and the typical example is the massive, in the case where you have massive gravitons. So if you consider, so you've seen this formula probably, or I don't know if you've seen this formula, but well, actually I think in the cosmology talk there was this formula for GR. So in GR, so if you have your gravitational field propagating in a cosmological background, your tensor field, so your gravitational wave, will satisfy an equation like that, or at least that's the Fourier transform of the gravitational wave, will satisfy some equation like that, where this term here will be 0. When we say we have a massive graviton, we are essentially saying there's an additional term here, something that's where this term is what we will call the mass of the graviton. And this comes essentially because if you look at wave equations for massive particles, they always have they take essentially this form. And this factor here, a to the square, is because I'm in a cosmological background, so this will be the scale factor of your background. Of course, locally, essentially a is equal to 1. The other rates you can neglect it, so you end up with just two derivatives of cu square, q square, where q is the wave number, because I'm working in Fourier space here. Something I have to say when I write an equation like this, and this is, for example, LIGO, and that's the part where I was talking about in practice, sometimes you might have propagation plus generation effects. So here, for example, LVK mostly only focus on this equation, for example, to constrain the mass of the graviton, but you might notice there's only H plus and H cross here. But for a massive graviton, in reality, there's 3 additional degrees of freedom. So there's a scalar mode and 2 vector mode as well. And we don't really look at them, and they might, depending on how they are excited during the merger, for example, of a binary particle, they might be important. The reason why we normally don't consider them is, again, because these theories, when you go to the full nonlinear theory of mass and gravity, just open the paper and you'll see how crazy the theory looks like, the full nonlinear. So that's why in practice no one has actually looked into in detail how adding the additional degrees of freedom will modify your theory. But anyway, if you only look at this propagation part, the main important point that you can get from this equation is that you modify the way waves travel, so the velocity of propagation. And in particular, what happens is that you get, well, you can derive this from this equation, that different frequencies of your wave will propagate at different frequency, different velocities, sorry. So when the mass of the graviton goes to 0, essentially this term goes to 0. So because this goes to infinity, lambda, where lambda here is essentially the quantum wavelength of your massive graviton, so it's related to 1 over the inverse of the mass of the graviton. So this term for masses, when the mass goes to 0, this goes to infinity, so this goes to 0, this term, and you end up with velocities that are equal to c, like you have in normal GR. But in this case, you'll have basically different frequencies of your wave as they propagate over time. Different parts of your wave will propagate with different speeds, so you will see a dispersion with respect to what you will see in pure GR. So this calculation is a bit annoying to do, so honestly I never done it myself, so I decided to just show the final results. So but the calculation of what this modifies the phase is shown in a paper by Cliff Wheel from '97, where essentially what is shown there, essentially by solving this wave equation, is that in the waveform at leading order, this leads to a term of this form, where it also looks like a correction to your post-Newtonian waveform. But what is important here that I wanted to emphasize is that now, so you get this parameter here, in this specific case, which is if you want how strong this correction is with respect to GR, will depend essentially on 1 over this quantum wavelength. If you want, it's proportional to the mass of the graviton square, but also depends on the distance of your binary. And that's basically telling you, that makes sense, right? Because here the point what you're actually detecting is a wave that was emitted at some source, and then as it propagates, right, the different parts of your wave, the different frequency of your wave will propagate with different speeds. And so the larger is the distance from us to this event, the larger will be this modification, so the more dispersion you'll see in your waveform with respect to GR. And so that's why this is proportional to the distance. So events that are farther away will be better to constrain, for example, the mass of the graviton, or at least this propagation. Okay, so that's it. So I gave you these 2 examples to show you that at least in a post-Newtonian regime, a lot of these modifications, you can add them basically on top of a post-Newtonian waveform, right? So you've already seen that in the inspiral regime, for example, you can write your waveform, right, in terms of an amplitude, the Fourier transform of the waveform in terms of an amplitude times some complex exponential factor with some phase, where this phase you can write them as an expansion in a post-Newtonian terms. So I wrote this in a generic way, where this term here is the point particle term, so it's the Newtonian term of it's the leading order term that you get in GR. And then in GR you'll get also different terms. So this psi 0, for example, is 1 in GR. And then this term, for example, is the first term where spins appear. For example, in this term you have some terms, and you'll have, for example, the quadruple moment of your binary, as I mentioned, etc., etc. I added this term here, and here is what normally we call the negative Pn order terms. So something I find, these terms are quite interesting, because if you detect ever something like that, it means that necessarily there's some new physics beyond at least vacuum GR, because in GR everything starts at psi 0, and then you have higher order terms. So these terms, which are more important in the early inspiral, like I was saying, necessarily imply some new physics. because you don't have any of these terms, any of negative Pn terms in GR. They can either mean, for example, dipolar radiation, but as I will also mention, non-vacuum environment, so some environment like, let's say, the effect of an accretion disk in general can also lead to these negative Pn terms. Not necessarily at -1 Pn, but they lead in general to negative Pn terms. So what has been proposed is that because a lot of theories, you can, in a post-Newtonian sense, you can write a lot of your theories in this way. You can write your theories as an expansion in the post-Newtonian terms. A generic way to try to test these theories without having to do specific calculations for specific theories is that you modify your GR waveform by just adding a phase term, basically, that has some power in F, right, that represent different Pn orders, with some parameters, beta G, J are just some numbers that will depend on the specific theory if you do the proper calculation. And something else you can also do is modify the amplitude of your waveform. This normally is you never see it really done because the amplitude is much harder to constrain than the phase. So basically, for example, in LVK papers and in most papers on this subject, there's no real constraints on these amplitude corrections, just because the amplitude corrections in general are much weaker because, you don't really constrain very well the amplitude of your gravitational wave. You constrain very well the phase evolution, but the constraints on these parameters were actually, and they are highly degenerative, for example, just calibration errors, for example. So in general, you don't consider them. But you could add them if you wanted. Okay, just to give you an example so I'm going to forget about the amplitude corrections and just use what is normally used the most, which is just consider corrections to the gravitational phase. So these are a table taken from this paper where they basically, in this table, you can see different different effects from beyond GR effects, link them to some beyond GR theories, and tell you, and here basically in this table you see at which Pn order these different effects enter, and well, if you go to the paper, you'll see there's a mapping of these betas here with some specific numbers that you get from these different theories. So if you, for example, would constrain the -1 Pn term, then you can go to the specific number for the specific theory and try to constrain the parameters of this theory. I will show you an example in some slides. So for example, the scalar dipolar radiation I was talking about happens, for example, in this Einstein-Dilaton Gauss-Bonnet theory. In scalar tensor theories, the massive gravity is essentially here, so it's a +1 Pn term. But also you can have basically terms appearing a bit all over the place in Pn, depending on the specific theory. So the idea essentially is, if I do this test in a completely model-independent way, so I just try to constrain these betas, for example, for given Pn orders, then in principle I could go back to this table and try to constrain given theories. So this has been kind of the game that has been played by the LVK, and I guess this will continue to be like that in LISA and future detectors. So to give an idea of this modifies the waveform, so I took, unfortunately, so this is a paper actually I think from last week, so this paper came right at the right moment because I know I have some plots on this paper which was very useful for the talk. So it's mine, it's not my own work. So these are people at the AI. And so this waveform essentially shows you an example of if you add a 1 Pn correction, such as the one that you'll get from the massive graviton, all these will modify the waveform that you see, the inspiral of the waveform that you will see in your detector, so in this case, H+. And so, well, these delta size 2 is basically the corrections to the Pn, to the amplitude of the corrections to the 1 Pn order phase, essentially. And well, you see that there's basically this modifies essentially the phase of your gravitational wave, right? Depending on the amplitude of these corrections. But something I wanted to point out that is important is when you do that, so all of this is valid in the INSPAL, right? So you always, when you do a test like that, you always have to somehow link this INSPAL to the merger ring down, that in principle you only know, well, you have a model in GR and you're adding on top of it a correction in INSPAL. So somehow you have to taper this correction and make it smoothly go to 0. And the way you do it is essentially arbitrary in reality, right? I mean, you just assume that your PN waveform is valid up to somewhere close to the merger, and there you smoothly go to 0. But this, I mean, a full non-beyond GR theory will probably not be something like that, right? It will modify here, perhaps it will modify the merger ring down, etc. So this is, let's say, the caveat of these tests, of these parameterized tests, where you're just adding a correction in a given part of your signal. So even though you're doing that and you can constrain it, you're not really using the full power of constraining the full waveform in reality. That's the same if you only do tests with the ring down, right? If you only do tests in the ring down, you are forgetting that the theory might also modify the INSPAL. So it's a useful way, but there's caveats about it, and it's a bit, at the end of the day, you might say it's a bit more conservative. The constraints that you put are a bit more conservative than what you'll probably get if you are considering a full theory. So the LVK basically already does these tests where they add modifications to the PN waveform. So these are the latest results that they put in in this paper. So this is the paper of this big large SNR event. And what this plot shows you is the constraint. So, well, the LVK writes a bit differently than in the PP approach, but the idea is similar, is that for a given PN order of your phase, you essentially, so this is the phase at a given PN order, so the 1 year, for example, will mean 0.5 PN, etc. You add corrections, you are computing the deviations from the GR phases. Something I should point out is that the -1 PN and the 0.5 PN terms, there's no GR term for this case. So what this term, for example, means is an absolute deviation at -1 PN order that are added on top. Okay, so I mean, from this plot, something that I can point out, for example, is at -1 PN, which is this term, there's like a very strong constraints coming from this event, and this event is essentially the binary neutron star. And the reason why the binary neutron star is the best one to constrain this -1 PN is essentially what I was saying, right? Is that the -1 PN is more important in the early INSPAL, and the binary neutron star, because it's a 2 roughly two solar masses, total mass in total mass event. The frequency, you can see really the very early INSPAL in the LVK band. So you can measure it very well because it's the dipolar radiation in this case, the dipolar term is more important in the early INSPAL. Another point I wanted to make is when you do these plots, so these are upper bounds on these parameters, when you do these plots, the way it's being done at the moment is you take one of these deviations, you add it on top of your waveform, and you constrain it to some Bayesian analysis. And you do it one at a time. The reason why it's done this way is because if you will add all these parameters at the same time, you will basically get no constraints at all, because everything is correlated with each other. So the only way to constrain it in practice right now, and probably also in the future, is to do it one at a time and to check if there's some deviation at a given PN order. That's something also, there's a caveat here that I was mentioning, is if you see a deviation, for example, let's say at 1 PN, if doing a test in this way, it doesn't mean necessarily that the deviation is exactly at 1 PN. Because even the 1 PN term might, the deviation in this 1 PN term might be detecting a deviation in some other part of the waveform. Because all these terms, the PN terms, they are not really orthogonal to each other, right? They all come roughly in the same place in the waveform. So it's not that trivial, actually. You can do this test for constraining, let's say it's easy, and you can interpret it as deviation as a given Pn order, but if you detect something, it's going to be a completely different game to try to get out, to actually figure out what is this deviation. So for Lisa, there's since there was this paper last week, I decided to show this plot because I think, I think the first paper that's looking in a Bayesian way what Lisa will, what are the prospects of Lisa to constrain these different parameters. And so here you see results for different events. So this is the total mass of the binary. I think the mass ratio here is close to 1. I think it's not exactly 1, but it's close to 1. So these are supermassive black hole binaries with some given masses, some given SNRs. And there are several things I want to point out here. So first of all, you see that the color, so each color here is basically a different total mass. And you see that, for example, at -1 PN, the best event to constrain this one is not necessarily the highest SNR one. It's actually the lowest mass. But this trend switches when you go to IPN. So essentially, this is related again to what I was saying. So it's not really only the SNR that matters here. It's really what you see of this event in the band of your detector. So, for example, the 10 to the 4 solar mass black hole, most of what you see in the Lisa band is the inspiral. So you don't really see the merger that happens after outside the Lisa band. And you see a lot of the early inspiral of this event, and that's why you can constrain very much better. This event is the best one to constrain essentially the -1 PN term. The IPN terms, right? So the IPN terms, they are more important. The higher the PN in general, the more. IPN terms, they are more important the closer you get to the merger, essentially, right? So because they correspond to higher powers in velocity. So for IPN terms, the events for which the merger is right in the bulk of your detector, these are the best ones. So because here for these events, for the 10 to the 6, for example, the merger happens almost at the peak of the bulk of the Lisa band. So most of the SNR is coming from the merger, right? And that's why this event, the 10 to the 6, solar mass event, is actually the best one to constrain these IPN order corrections. So essentially what this is telling you is that if I want to constrain very well all these PN order parameters, it's good to have, a very large range of masses, of black hole masses, such that I can constrain different parameters very well. Going back to this plot, something else that you might notice here, if you look at the current LVK result, is that the -1 PN, corrections, the constraints that prospective constraints with Lisa will be in principle 4 orders of magnitude better than current LVK, which seems great. However, again, I think that's something that you always have to keep in mind, is that this bound is what I'm showing is just a bound on a random parameter that I put in my waveform, right? But if I want to actually give meaningful results, eventually I have to map back to some theory and say what this means for a given theory in terms of constraints for a given theory. And so I'm giving you this plot. So this plot comes from this paper where they looked at prospective constraints with given detector scenarios over time. So this plot is very busy. There's a lot of information in this plot. But the main idea is that what they look at is constraints, for example, with current LVK, and then they go to next 05, 06. So these are future runs of LVK. Then here in 2035, you have Lisa. I think this 2040 Lisa, I think this means Lisa extension. So it's imagining that Lisa could go over for more than 4 years. And this includes, for example, next generation ground-based detectors. And what they are showing you here is the constraints on a given parameter. In this case, is in the coupling constant of this theory called Einstein-Dilaton-Gauss-Bonnet. So it's one of the theories that Susanne considered the most in the first lecture. With different sources. So all these SCOBH, they mean stellar origin black holes. So they are LIGO-like, LVK-like black hole, essentially. This MB here means multi-band, so these will be stellar origin black holes that are seen both in ground-based detectors and in the LISA band. MBH means massive black holes, so supermassive black holes tend to the LISA ones, let's say. Well, and then they have different populations for these massive black holes, and because they also use simulations of catalogs of simulations of population of black holes to get an idea of whether you could, how well you can constrain these theories for given black holes that you will detect. So these are different. So Q3 and POP3 are related to all these massive black holes were formed. In general, POP3, for example, you will get a lot of less massive black hole, let's say. And these constraints here are cumulative constraints, so they take into account that you will, in principle, use all the events, all the constraints, and pile them together to get better and better constraints, and that's why the constraints tend to go down in time. So what I want to emphasize in this plot essentially is that the current LVK bounds on this parameter based on the dipole on the minus 1 pn minus 1 pn constraints are basically this line. This line here is some other constraints not coming from gravitational waves. It comes from X-ray binaries, but there you could say that there's a lot of systematics in these constraints. So let's say the constraints that we believe the best are, I will say, is these current ones from LVK. And the constraints that will come from massive black hole binaries, even though in the minus 1 pn term, you can constrain it much better with LISA in principle. When you transform these, so the corrections to your minus 1 pn to a specific parameter in the specific theory, because this beta here scales as a power of, as 1 over the total mass of your system to the 4th, if you have very large masses, basically this parameter is always very small. So your constraints on alpha will be quite weak. So essentially that's why with massive black hole binaries you don't really do better than with LVK. So this is also intuitive in the sense of these specific theories, basically a theory that includes the corrections to GR related to higher curvature terms, right? And you might know, for those of you that have, at GR, that the larger a black hole, the smaller is the curvature of that black hole at the surface close to the horizon. So essentially it means that very, very massive black holes, they have a very, very small curvature, essentially. Which means that if you're looking at deviations that are related to higher curvature corrections, the smaller the black hole, the better in terms of the corrections. Well, the stronger the correction to GR they give you. So this is true for any type of parameterized test that you do. You always have to be careful at looking at numbers and not overinterpret what they mean, because I think they only really have a meaning when you map them to a given theory and you say something about it. Before doing that, they're just telling you that your date is compatible with GR, but it's not telling you much about specific theories before you do the mapping to a given theory. For the massive graviton, so because these are the two examples that I gave, the dipolar emission and the massive graviton is also some of the most, the ones that you see the most in a lot of LVK papers, for example. And also this is a particular example where LISA can do much better than LIGO. And in this case, the reason, so this is a similar plot where the current LVK bounds are essentially in the 10 to the minus 23 electron volts. So for those of you that have read particle physics papers, mass in particle physics normally measured in electron volts is a better, it's an easier measure of particle masses. So 10 to the minus 23 is the current bound on the mass of the graviton, given the current observations by LVK. With massive black hole binary with LISA, if you convert the prospects of the 1 pn, the constraint on the 1 pn correction, and convert it to a constraint on the mass of the graviton that is basically related to the Compton wavelength here, you get something that is around 10 to the minus 26. And that essentially is related to the dependence on the luminosity distance of these events. So most of the events that LISA will see, in principle, they will be seen at much larger distance. Much larger distance than what current LDK, than most of the events that LDK is seeing right now. So LDK, for example, right now, most of the events are up to 1 gigaparsec, a bit larger, let's say 5 gigaparsec at most, while a lot of the events for LISA will be larger than this, right? So a lot of the massive black holes that LISA will see. This is for massive black holes, not for M. For M is a bit different. And so this essentially means that because you can see, because essentially what I was saying, that propagation effects, they are effects that build over the distance. If you can see something farther away, that will mean better constraints on your events. Yeah.
Sorry, just coming back to the previous point about, I think it was just a slide before, sorry. Yes, this. So the fact that, you need to, oh, where is it? Okay, you make this point, yes, this one. So I'm not sure, can you elaborate on that? Because it kind of sounds like you're doing all the nice hard work of like being theory agnostic, but then you have to go back to...
Yeah, the point is, well, there was a nice paper, I think it's by Michael Isner, and I don't remember who else, that they made this point that I can always parameterize in a way that my numbers will give small numbers. Just put a parameter that you constrain and multiply it by a very small number. The constraints will be very small. They will look very small, just because you're, in some sense, adding a random way to parameterize. But then, if you want the parameter that you're constraining, then you want to compare it with some given prediction, like in this case, this one, right? And depending on the factors here, right? Because let's say you're constraining beta, right? But beta depends on both alpha and the mass, right? So the fact that I'm getting small numbers for beta, it's not necessarily because alpha is small. It can be because M is large, right? You see the point? So it's, constraining beta doesn't tell me much. It's like the magnitude of the constraint doesn't tell me much because I don't know all these beta depends, for example, on the masses, on the spins, etc. So in this case, because this beta, in specific theory, beta depends very strongly on the mass, like as a power 1 over m to the 4th. I can make beta very small by just putting m very large, and right now, for example, with LISA, you can constrain beta to be very small. That's what you can do. But because I can already make beta very small by just putting the large mass, alpha can be very large while still keeping beta quite large, let's say. Alpha, quite small.
But so doesn't that sort of kill the theory agnostic direction? No,
I'm not saying that it's pointless or first. You should do it because that's the practical thing to do. But you should always be, you should not, again, just not overinterpret those constraints, right? When someone tells you the constraint at minus 1 pn is 10 to the minus 7, that doesn't really have a big meaning before you actually tell me what does this mean for specific theories, right? Because the 10 to the minus 7, I can have something, a correction at this 10 to the minus 7, not necessarily because the coupling constant of the theory is small, but just because I have very large masses, right? So that's the point. Okay. So I think I still have half an hour, so I'm in good shape, 10 of time. Okay, is there any question about this part? All this part of the parameterized test?
Okay, so I think for the second to loudest LBK event so far, they found these sort of deviations in PVM parameters near the merger ring network, like the stitching to whatever. But then they show, okay, if you change the noise realizations a certain number of times, you can get this sort of effect. Yeah. If we actually have a beyond GR theory, do we expect the difference in these sort of, agnostic parameters to be significant? Is the only way we can make a significant statement if we completely rule out, the effect of different noise realizations? I don't know. I guess the question is...
Honestly, it's hard to say because, I think all of these, all of the testing that's for parameterized tests and any test it's easy to constrain and to say, even if you have a deviation, then you can say, oh, it was because of noise, or we didn't put precession, spin precession, etc. But then if you see a deviation and you're not able to explain it through noise or through systematics. I think it's very hard to do the back game. Honestly, I'm not going to tell you how to do it because I don't think anyone actually knows. I mean, the best way you can do it is then to do a bunch of predictions with different models and then do model selection and try to see which one is the best theory that explains. But I feel, well, no one is really worried yet about this because the deviations so far, the one that I've shown up, they seem to be explained by noise features or systematics. So far we are okay, but I think once we see a deviation that we cannot explain, then it's going to be like the next day 100 papers on the archive trying to explain it with different theories, I'm pretty sure. So, and I think the only way is to then we have to start making actually models, waveform models for given specific theories and do proper model selection and try to explain it. So it's not going to be a straightforward thing to do, I think. Yeah.
But I guess, so if there is a beyond GR theory, there's a true underlying theory, then the expectation is the deviation will be large enough that it can't be...
Well, it has to be, if you see the deviation, then of course it has to be something that is large enough. So, for example, right now what we know, for example, from, well, let's say from these current bounds on for this theory, is that if you see a deviation in LISA, for example, it's very unlikely that, I mean, it's unless we are doing something very wrong, it's not going to come from these Einstein-Dilaton-Gauss-Bonnet because the constraints that we have are already completely constraining, telling you that any deviation in LISA from this theory is extremely, extremely small. But it could come from, the problem is, of course, in these things is that, I mean, we have a limited knowledge of all the possible theories in some sense, right? I mean, we don't know, it's not like we know every single theory that you can build in principle. So, yeah, it's, yeah.
Thanks.
Okay, so all that said, now I want to go to the beyond vacuum GR, as I was saying, because, and so that's an important point because, well, besides these issues that I just said of actually claiming the detection of beyond GR, which is a very difficult thing to do, there's also the issue of if we see a deviation, it might be noise, might be systematic, but something that we cannot also forget is that black holes do not, all of these calculations assume that you are in vacuum, right? Black holes live in basically complete vacuum, which is not true, right? I mean, astrophysics is very messy. So there's been this question for a long time of whether environmental effects, and that can mean accretion disks, an additional body close to your binary system. You could even think about dark matter, and I'm sure you can think about other environmental effects where they can spoil this claim that we can do precision tests of gravity. So there was a very influential paper 11 years ago. So this is a very, if you're interested in the topic, I think that's the best introduction paper on the subject. It's a very long paper that goes through a lot of environmental effects. And so the paper is called Can Environmental Effects Spoil Precision Gravitational Physics, Astrophysics in this case. And I don't know if you know this rule, but whenever there's a question in the title, the answer is always no. So they claim, which is not, well, I think it's a correct, if you go through the calculations, it's the correct claim, is that environmental effects are unlikely to spoil most of the precision tests that we can do within a broad class of scenarios. So although the conclusion from this paper is that in principle environmental effects might not be that important and we might be able anyway to do precision tests, it doesn't necessarily, this is not equivalent to saying that environmental effects are not detectable. So the general conclusion from the paper is that environmental effects, they are likely to be uncommon or at least too small for neither equal massive black hole binaries. That's mostly for two reasons. One of them, massive black hole binaries, you see, well, most of what you see is like the late part of the inspiral and the merger. A lot of the environmental effects, they mostly affect early, the early inspiral. So for massive black hole binaries, they are most likely too small, but also in a lot of cases, it seems that as you approach the merger, a lot of your environment is basically thrown away just because of the dynamics. So by the time you see your massive black hole in the LISA band, most likely, and the likely here is, of course, should be taken with care because it's not like we know for sure. But most likely for massive black hole binaries, when you see them in the LISA band, the environmental effects are not super important. That's not exactly true for PTA, for example. So, for example, there's been claims that what you see in PTA might include, because in PTA you're not seeing exactly that power of F to the some number. You're actually seeing something that is shallower. And there's claims that this could be because of environmental effects, essentially because, again, in the black holes, supermassive black holes that you're seeing in PTA, most of the signal should be coming from early in spiral of supermassive black holes, where environmental effects might be more important. That said, at least the case where the environmental effects might be much more important and could be detectable in some events are MRIs and also, well, MRIs, IMRIs. IMRIs here means basically something that is not extreme mass ratio, not 10 to the minus 5, but let's say 10 to the minus 2. So sometimes there's this distinction between the two cases. But it basically means something with a very small mass ratio. And essentially for MRIs, what is important for MRIs is basically the fact that MRIs, you see them in band with a lot of cycles. And so even if environmental effects are small, and that's also true for beyond GI effects, for example, MRIs are quite good at constraining small effects because you see them going in band for like tens of thousands of cycles, right? So any small effect will build up over time and might become detectable. And the part of some events, especially this is mostly related also to accretion disk physics. The claim is that, for example, AGNs, so most of massive black holes in the universe are quiet. So I'm not an astrophysicist, so if there's astrophysicists in the room and I say something wrong, correct me, please. But most of the supermassive black holes in the universe are quiet, and roughly 10% of them seems to be AGNs right now. And so you can, in principle, link something that has a strong accretion disk physics around the supermassive black hole only to roughly 10% of all the supermassive black holes, which might mean that only a small fraction of supermassive black holes have a sufficiently dense environment around them that it could affect the MRI. So, and because you might see MRIs coming from all kinds of black holes, not only, unlike electromagnetic observations where you basically most only see the ones that are emitting light, right? With gravitational waves, you can even see the ones that are quiet in the electromagnetic band. So if MRIs are coming, if 90% of supermassive black holes are a very almost negligible environment around them, then it means that most MRIs will not be affected by environment. So this is basically the main claim from the paper by Enrico Barros et al. So there's different types of environments. That said, this basically tells you that I don't really need to worry too much about environments, at least it seems so. But it might be detectable in some cases, and in those cases it might spoil precision physics. But you can also see it in another way, is that if I actually detect something, right, it also means that I can learn about the environments around black holes, which is something perhaps in a better way that I can do right now with electromagnetic waves. So there's different types of environments that have been considered. I'm going to describe some of them. So what I would call non-exotic black hole environments. So these are the ones that you would expect just from pure astrophysics. So for example, perturbations from a third body, if you have an MRI, and a third body with mass m star, some distance r away from your binary system, this will perturb your binary system, your MRI system, and will, in principle, tidally perturb your system. In particular, it has been shown that it can lead to something called tidal resonance, so at some specific frequencies, essentially kind of kicks your binary and changes the parameters of your binary very quickly. So this happens at specific frequencies in your system. If you want details, you can go to the original paper by Beatrice Bonga, Wan Yang, and Scott Hughes. But the main conclusion from that paper is that this can lead to at least a dephasing that is ordered for radians. So in principle, that means that in principle it's detectable. In particular, it strongly depends on the, I don't know, here this M should be M star, actually. So this M should be the mass of the companion. So the larger is the companion, the larger is this third body, the stronger is this effect, as it will make sense, right? Because the larger is the third body, the stronger is the tidal effect. But it also goes as the 1 over r to the cube in distance. So this is basically because tidal effects, they go as 1 over r to the cube. So the closer is the third body, the stronger is the effects, which you might expect. Another effect is, of course, if you have an accretion disk, this will create, essentially, this will affect your small body. And the main effect here is something called planetary migration. So, well, this is something typical, for example, in solar system things. I don't remember the right word. But the main idea of this is basically, imagine that you have your small object here moving in accretion disks. This essentially will perturb your accretion disk, so it will create these wake profiles, so these spiral arms. And so in this planetary migration is something also, well, it's related to something called also dynamical friction. It's basically related to the back reaction of the fact of these perturbations on the small body. So you create these object as it moves in the accretion disk. It creates these spiral arms, and the spiral arms create a torque on the small body, and basically change the angular momentum of your small body. And you can add it on top of the gravitational wave. It will add up on top of the gravitational wave emission. So these are what I will call the most, what you should expect to be there for some events at least. But perhaps because it's a fundamental physics lecture, there's also other interesting environments, and I think these ones are, well, I'm personally quite interested in those, but what I would call perhaps a bit exotic, that are related to dark matter. I'm calling them exotic, but I think sometimes we should, I don't think they are as exotic, for example, as considering beyond GR, because we know dark matter is there, right? So we know dark matter is a problem, and it is there for sure. So calling it exotic it's a question of, I think, of who you talk with. And in particular, you don't know much about how dark matter, how dark matter looks like, or the profile of dark matter at small scale. Most of what we know about dark matter comes from large-ish scale structure, so scales of galaxies. We don't know much about how dark matter behaves, for example, at the scale of supermassive black holes. And that's the reason why there's really, dark matter could be almost anything, could be particles with almost any mass, because we cannot really constrain the small scale structure of dark matter. So that leaves room for a lot of possibilities. But at least in some cases, you can form what I call dark matter spikes around supermassive black holes, and that will happen naturally if you have your supermassive black hole sitting in the center of your galaxy, and as it accretes, it grows. As the potential of the gravitational potential of your supermassive black hole becomes more important, everything that's around tends to fall towards the black hole, and so you tend to form higher densities of dark matter around your supermassive black hole. So, well, this is work that goes back to 20 years ago. In particular, this could be quite interesting if you have highly dense structure of dark matter in the center of galaxies. They could lead to, they could affect MRIs, for example, and you could try to detect them with MRIs. Another subject that, well, I'm particularly quite interested in is called boson clouds. So this is basically, if you want, a structure of a particular type of dark matter related to having extremely light bosons. So when you have extremely light bosons, there's something that can happen around spinning black holes called super-Rayleigh instabilities. Essentially, the idea here is that these fields can extract angular momentum from the black hole, and this angular momentum is transferred basically to a sort of cloud of these particles. The structure is quite interesting. It looks basically like an atom. That's why it's sometimes called gravitational atom. If you're interested in this subject, you can, well, we have a review on the subject. I invite you to read about it. But the main idea here, the point I want to make, is that there's at least proposals of ways to form dense environments of dark matter candidates around black holes. And so this has been the fact that you can have this dark matter structure on black holes And if you detect them, it could tell you a lot about dark matter physics, right? Because unlike the current observation of dark matter, that again come mostly from large structure, like large-scale structure, if you detect something at the scale of supermassive black holes, you can really tell about the small-scale structure of dark matter, and that might allow you to constrain different types of dark matter candidates, and well, even in the best-case scenario, detect it. So there's some effects that I'm going to go through. I'm going to focus mostly on dark matter, but it's kind of generic what I'm going to say. That are the most important environmental effects if you have a dense environment around the black hole. And the most important one is essentially something that I think it's quite, I mean, it's well known, and it's quite important in astrophysics as well, which is called dynamical friction. And the essential idea, the essential intuition is also similar to what I said about planetary migration, is that if you imagine an object that is moving inside the medium with some velocity v, right? As this object moves, it creates a wake, a perturbation behind it, right? Because so you tend to accumulate things behind you because of your gravitational interaction, and this overdensity behind this object as it moves will create sort of an effective force, right? A force due to the gravitational interaction. So notice that these are pure gravitational interaction effect, right? It's just as I move in the fluid, things will tend to go to my back, and they will push me back due to gravity, essentially. And in this case, where you have an homogeneous, well, this is a simulation with an homogeneous uniform medium, this tends to slow down, basically, the object as it moves inside this medium. So it's an effect that is similar to gravitational emission or other dissipation effects. So at least for, well, if you, this, of course, there's been a lot of work on the subject, but just to give you some formulas, if the energy that you dissipate in a uniform, asymptotically uniform medium, in considering non-relativistic velocities, the energy that you dissipate due to this dynamical friction effect is proportional to the density of the medium. So the more dense the medium is, the stronger is the effect, as you would expect. It scales as the mass squared of the object moving inside it. And well, it goes roughly as 1 over the velocity of the field. There's also here a function. So this function here that I'm putting here will depend on the type of medium. So it will depend when there, for example, these are collision-less particles, a medium where interactions are strong, whether the Compton wavelength of these particles is large or not, etc. But in general, if I consider these to be order 1 and the density, constant density medium, roughly speaking, the effect of the dynamical friction, so this is the rate of change of the radius of your orbit, which is divided by the rate of change of the orbit due to gravitational emission. To give you some numbers, this effect of dynamical friction tends to be larger than gravitational emission if the density of your medium is sufficiently large, and the radius of your orbit is also sufficiently large. So as the orbit decays, right, as this orb goes down, this number will also become quite small. So this is mostly important in the early spiral. And of course, you need to have a sort of strong, dense environment. Another effect, although this effect is subdominant to dynamical friction in general is really the most important effect of all. But there's also other effects that you might need to include them if you want to be accurate, and one of them is just accretion. So if you have your body, in this case your black hole moving inside a medium, of course this black hole will accrete matter as it moves, and it will change its mass, right? And so if you do a very simple calculation, in this case I'm again considering collision-less dark matter, because that's an easier calculation. In this case of collision-less fluid, the accretion rate basically scales as the cross-section of your object times its density times its velocity. For example, for collision law, if your medium, there's strong interactions in your medium, this formula is not correct. So in this case, you need to use what is called the Bondi Bondi oil accretion rates. Anyway, but the important point is, again, this scales with the density of your medium. So everything scales always with the density. And also with the mass squared of your black hole. So now, very simple calculation that you can do if you only use Newtonian physics. So the orbital energy, the orbital angular momentum of your particle in a circular orbit is given by this formula here. Sorry, I messed up the formula. So yeah, MP should be mu here. So I took it from different slides and a different notation. But so now if you neglect dissipation due to gravitational emission, etc., of course you can always add it on top if you want, but this is just to show you a simple formula. If you just take the derivative of this, right, and consider that the mass, so this is the mass of the central object, in this case, for an memory. If you consider that the only thing that changes is the mass of your small body because of accretion, and also the orbital radius changes over time, you take the time derivative of this, you'll get, and you consider that angular momentum is conserved, the total angular momentum is conserved, you'll get essentially that the rate of change of your orbital radius, basically is proportional to the accretion rate. Now, if you put some numbers, again, you get something that as the orbital radius increases, it becomes more important. And also it's proportional to the density. But, well, this number, for example, is 10 to the minus 2 here for the same numbers that I used for the dynamical friction, while dynamical friction was 3. So these 2 orders of magnitude smaller than dynamical friction. So it's in general less important. Okay, now, so if you put all of this together, so if you compute all of the orbits affected both by the radiation reaction due to gravitational waves, plus dynamical friction, plus accretion, and you can also include the fact that your, in this case, dark matter profile, for example, has some potential, right, has some cell gravity, so you can include it to be completely correct. Again, using just Newtonian, some basic concepts of Newtonian physics, you have that your orbital energy is just the sum of the kinetic energy plus potential energy. You can compute your frequency of the orbit, go through the calculation of phases, gravitational phases, using, well, I think I showed the formula some slides ago. And here, for the sake of simplicity, consider a medium that decays as 1 over some power of r with distance. This r is just some typical scale related to the typical size of your profile. You'll get to the conclusion that your PN the corrections to your waveform in the PN phase will essentially be of this form. So essentially, for the dynamic, if you have a constant, just simply consider that gamma is 0, so that this is a constant density medium. Your dynamical friction term is a minus 5.5 PN ordered correction to your phase. So it's a very small PN correction, very negative PN corrections. Accretion enters at minus 4.5, and what I'm here calling gravitational pull. Gravitational pull is essentially the correction due to these terms, to the fact that I'm adding the gravitational potential of the dark matter density in this case. These enter at minus 3 PN. If you actually put numbers in all of this, so this is an example that shows how the orbit, the energy change of the particle changes over one orbit, as a function of the radius of your orbit, for given parameters of the density of the masses of your system. So this is an memory with 10 to the minus 3. This is the contribution of gravitational emission that becomes more important as you get closer to the merger. You see that dynamical friction dominates over other environmental effects, and it becomes more and more important as you go far away. So as you go far away, what dominates the evolution in general, that's actually true also in other cases, not only in dark matter, is not gravitational emission. What brings things together is actually dynamical friction in this case. Okay, so that said, so I only have 2 slides, I'm almost finished. That said, there's already been studies of looking into these effects also more seriously than what I did in these slides. So what I did in these slides were purely Newtonian, very simple. But there's been a lot of work in this subject in trying to develop, making better predictions. In particular, there's this work where they look at different effects. So in this case, they look at the environmental effects due to an accretion disk, due to these dark matter spikes that I talked about, and these gravitational atoms, which are these boson clouds that I also mentioned. And so this shows you for a given system that they consider, so it's an MRI with supermassive black holes 10 to the 5, 10 solar mass for the small one, and SNR of 15, they consider a system like that. And if you plot the typical density as a function of the distance to the central black hole for different environments, so accretion disks tend to be, well, these are using the particular model for dark matter spikes and also for new gravitational atom case. You can, in general, reach much higher densities than accretion disks with these, within some models of dark matter. Of course, it depends on the particular models that you use. But within reasonable assumptions, you can actually reach much higher densities with dark matter than you can reach than the typical densities of accretion disks. And what they did essentially is do injection. So they injected these environmental effects. They included these environmental effects in gravitational waveforms. And they did parameter estimation studies where the idea was you inject a signal that has, for example, a dark matter spike profile around it with these environmental effects. And then you recover it both with a waveform that has this effect on it, and you compare it with the case, for example, where you do the parameter estimation with a vacuum template. And then you do model selection and you see which one fits better this signal. So for example, in this case, you have signal which has a dark matter spike, and then you do recovery with the dark matter spike template, but also recover it with the vacuum template, and you compute these base factors, which the larger is the base factor, the more, the better the model, well, in this case, the dark matter spikes template will be much more preferred in terms of a fit to the signal than the vacuum template. So the fact that you see 34 here means that you can actually say that if you have a dark matter spike in your signal, and you recover with a dark matter spike waveform that includes dark matter spike effect, these will be much more, will be a much better template than the vacuum template, because you get a base factor, and notice that this is log 10 to the base factor, so a base factor of 10 to the 34. So these are extremely large number, actually. And in general, so the general conclusion is that if you do it with different environments, you can, in principle, distinguish these different environments. This mostly comes from the fact that the different environments, they give you different density profiles, essentially. And because you see the spiral as it goes along, the effect of the environment will change over time, because the density is different for the different environments. That said, okay, there's a lot of caveats in this study. So this was a very rough, let's say, study where they only used Newtonian order waveforms, neglected things like spins, only consider circular or equatorial orbits, including eccentricity. So I think this is an indication, but of course there's work to do in terms of understanding this in more completely. And in particular, so this is the last slide. In particular, there's a lot of current efforts in developing environmental effects, and in particular something that, well, I'm particularly interested as well, and there's been a lot of developments in the last 2-3 years, is to include fully relativistic effects in environmental effects, so compute environmental effects, for example, using all the tools from black hole perturbation theory. So this shows you an example where we consider these boson clouds and computed the environment, computed all the perturbation due to the secondary will perturb the cloud, and you see these wake profiles that you also see in accretion disk physics. So it's kind of the same physics as the object moves inside these clouds. It creates these spiral arms, so these are quite generic effects. There's also, just last week, there's been a work looking into the effect of relativistic effects in the torque created by an accretion disk on the secondary. So I'm not going to say much more here. If you're interested, you can go to the papers and try to understand more. And also there's been, people have started actually, there's a work where with Alessandro and Hassan Calvati and other people that looking into actually parameter estimation of these environmental effects in a full Bayesian way, but where we use a fully relativistic waveform, so with few, and on top of it you add an accretion disk, well, migration torques essentially, and you can do P, so you are starting to do this type of studies. That said, I think there's a lot of challenges here. In particular, I think there's questions that really need to be addressed, such as how well do we actually need to model these environmental effects to say something about them, especially when you're talking about accretion disks, etc. The physics of accretion disks is quite complicated. So far, people have been using extremely simple models. For example, this is a model that has been quite used to parameterize migration torques. So basically, you just parameterize as a power law in the semi-major axis with some amplitude. There's also work on trying to understand the generosities between environment and beyond GR effects, as some of you have asked. But this is really, I really don't have answers for these questions because I think almost no one has looked into these things. And in particular, I think that's quite important, especially in this concept of a Lisa screw and perhaps something that some of you might be interested in working in is to try to see whether, in the context of the global fit, where everything is much more complicated than just a single signal and you can use it to do a test, whether environmental effects and beyond GR effects can be actually detected in this kind of test. So, okay, so for the slide, because this is the last slide of the lecture, and I really like quoting people. I wanted to leave this sentence because I really like it. It's a sentence from Maxwell, so the guy that wrote down the Maxwell equations. And essentially, just back then, they already had this notion that essentially physics is really about improving your measurements, even if you have zero theoretical indication where you're going to. And your goal is always going to the next decimal case of precision, and that's where new physics will probably be. So thank you.
So thank you very much again, Richard, to convince us that how challenging it will be to interpret any deviation of vacuum GR if we see one. Are there final questions for Richard? Yes.
Sorry, I'm just wondering, could you say a bit more on the last question you asked about how the global fit could affect how we model this? I don't know, do you have specific ideas that you're referring to?
Well, I'm not saying I have ideas.
Okay.
But in the global fit, for example, you'll have contamination from other sources, right? So it's not like a clean signal and that's it, like, for example, LVK has, right? You'll have many sources at the same time, and just systematics of the fact, for example, just the fact that you don't have perfect models even in GR, right? And you're trying to, for example, let's say you have a massive black hole on top of an memory, right? Let's say you detect your massive black hole, and with the best fits that you have for GR, you subtract it, and then there will be the residual just from systematics from the fact that you don't have really a perfect model that might affect measurements of environments and beyond GR, for example. That's an example where, and also just the messiness of the global fit is already complicated. I'm adding additional parameters, even just from a pure practical point of view of doing the global fit with additional parameters. Also, I don't think it's fully addressed.
Okay, thank you.
Any other questions before the break? Well, otherwise, let's thank again Richard.